Okay, 2.5, here we go. So we start out with some congruence properties, and these will look familiar because we have the same properties of equality, but these are properties of congruence. So we've got reflexive, symmetric, and transitive. So notice they have the little congruent symbol in parentheses. So it's really important that always from now on, if you're talking about the reflexive property, you got to say if you're talking about the reflexive property of equality or of congruence. And you can just do that with the little symbol, either the equal sign or the congruent symbol. So the reflexive property, in essence, is that anything is equal to itself. Well, that's for equality. And for congruence, it's anything is congruent to itself. I mean, so you have to have something that can be congruent to something else. So like a line segment can be congruent to itself, or an angle can be congruent to itself. So I'm not writing out a definition, I'm just giving you some little examples because they're so similar to the properties of equality. Okay. Symmetric is where we can flip around an equation and still have it be true. But this is just, instead of an equation, it's a congruent statement. So let's say that segment AB is congruent to segment CD. Well, if that's true, well then I can take this congruence statement and flip it around. So I could also say that CD is congruent to AB, segment AB, like so. Okay. And the transitive property of congruence. So this is, I think I used this example before. So if I have the same birthday as Abe Lincoln and Abe Lincoln has the same birthday as Beyonce, that means I have the same birthday as Beyonce, right? But since we both have the same birthday as Abe Lincoln. So it's that same kind of idea. So if angle A is congruent to angle B, and angle B is congruent to angle C, well, hey, both A and C are congruent to B. So that means they must be congruent to each other. So I can say, therefore, then, angle A is congruent to angle C, and that would be using the transitive property of congruence. Okay. All right, so we're going to do a two-column proof here in a minute. So a proof, we've already been doing these in essence with algebra, where we had where we just write the justifications for each step. And this is just an organized way of doing that, but there's nothing different. So a proof is going to be a logical argument using deductive reasoning. Okay, so we're going to go step by step and logically work through until we get where we want to go. And we're going to show how we got there. We're not going to make any jumps, any guesses, or anything like that. So I'm going to use the given information to get what I'm trying to prove. So in this case, it's just starting. This is an algebraic proof because we've just got an algebra problem here. So the given, and I'm going to put that as my first statement always. Okay. So that's always going to go in this first slot. Okay, I really like when you're writing your own proofs. I really like you to label each step. Okay, each statement is going to have a justification, or sometimes it's called a reason that goes with it, and it's really helpful if you see these are both labeled A, and then we'll do B and C and D and so forth, because sometimes the either the statement or the justification can get longer and things get misaligned, and it's hard to tell what statement goes with what justification. And this solves that problem. I always know, hey, statement A goes with justification A. Okay, so how did I know that? Well, just because it was given. Okay, so the first justification is pretty much always going to be just given. You have to start with some given info, and in this case, there it is, right? So I just copied it in there and said, hey, because they told me so, right there, right? Okay, and now I gotta somehow get to x equaling 2. So I'm just thinking, well, what would I do here? First thing I would do, I would try to isolate the x to see what x equals. So I'm going to subtract 4 from both sides. And you could write in the -4 on both sides, but what I'm going to do instead, well, I guess I'll write it really small here just to show what I'm doing, but I'm not going to put that in one of the steps. You could write 2x plus 4 minus 4, but I'm just going to write, well, after I subtract 4 from both sides, that puts me right there, okay? So this is going to be, I just subtracted the same thing from both sides of the equation, so this is going to be the subtraction property of equality. Okay, now I'm not going to write out property of equality, but I want to show that it is a property of equality, so there's my short version of doing that, okay? You can feel free to abbreviate subtraction if you want to, but if you do that, make sure you get that far, right? Or actually I guess you just need to go to the T, but you need enough so that we don't confuse it with substitution if you are abbreviating, okay? And then next step, I want to divide both sides by 2 to continue isolating the x over here. So that means I'll have x equals 2. Okay, and hey, that's what I wanted to prove, right? Oops, I'm off screen now. X equals 2, that's what I was trying to prove, so x does equal 2. So I got that from dividing both sides by the same thing. So this would be the division property of equality. Okay, one proof down. Okay, so that's a really simple one. That's really similar to the algebraic reasoning we were doing. We just didn't put it really in the boxes and label the steps, but that's all the difference is. That's what a 2-column proof is. Okay, so let's move on to an algebraic proof, a geometric proof, I should say. It just means we've got some geometry here. This isn't algebra, right? It's not using variables and arithmetic. Okay, so let's see what we got here. So I'm going to recopy the given info. I'm not even really thinking about what it says yet. I'm just going to recopy it right down here. So the given info is always going to go in the first step. And especially on here, since we got the stuff right there, it's totally fine to abbreviate. So I'm saying angle 1 is supplementary to angle 3, and then angle 2 is supplementary to angle 3. Sometimes your book will take, if there's 2 different given pieces of information like there is here, they'll split those up into steps A and B. But I don't care if you do that or not, it doesn't matter. You just have 2 given steps if you did it that way, but I just have 1 given step. That's my given info, okay? All right. So I'm trying to prove that angles 1 and 2 are congruent to each other. So the given info is that they're both supplementary to angles 3. They're not equal to, right, or not congruent to, so I can't use the transitive property right now. This isn't transitive. So what I'm going to have to do is think, well, what does supplementary mean? Well, that means that their measures, the sum of their measures would add up to 180 degrees, right? So I could say the measure of angle 1 plus the measure of angle 3 equals 180 degrees. That's from that first piece, right? Okay, and then I can, since it's the same kind of thing, I'm going to put this in the same step. I'm going to say measure of angle 2 plus the measure of angle 3 is also 180 degrees. Okay. All right, so that wasn't one of the properties that are covered in this section, but the reason I can write those equations is because I know what supplementary means, okay? So I'm using the definition of supplementary, right? So that is my justification over here. The definition of supplementary, I'm just going to write it like that. Some people might say the definition of supplementary angles. That would be fine too, okay? All right. All right, so now I've got some equations, so let me think what I can do with this, okay? So this is kind of interesting because now I've got, if I look at step B here, I've got 2 different things that are equal to 180 degrees. So hey, that means they're going to be equal to each other, right? So now I can say, okay, well, this equals 180 degrees, and so does this. Then those two underlined things equal each other. So I can say the measure of angle 1 plus the measure of angle 3 equals the measure of angle 2 plus the measure of angle 3. Okay. All right, so how did I do that? Well, one thing you could say is that you use the transitive property. If you have two things that are equal to a third thing, then those two things must be equal to each other, right? Like the Beyonce Abe Lincoln birthday thing. Like, right? If me and Beyonce have the same birthday as Abe Lincoln, then we have the same birthdays as each other. That is the transitive property. Okay, now it's tempting to say congruence, but if we look at this, we don't have a congruence statement here. We have an equation. Okay, so remember, if I just said like angle, if I wanted to say angle 1 is congruent to angle 2, then I use congruence. But if you have the measure of those angles, then you it's an equation. Measures will be equal. The angles themselves will be congruent. Okay, so I'm actually using that transitive property of equality. Some people might make the argument that, hey, wait, if 180 degrees is equal to measure of angle 1 plus measure of angle 3, can't I just sub measure of angle 1 plus the measure of angle 3 in for the 180? So actually, you could use the substitution property of equality here as well. Okay, so that is you'll notice that'll happen a lot. You definitely don't need both of those reasons, but either of them will work. There's two ways that you can justify getting from here to here. Okay, they aren't always interchangeable, but a lot of times they'll both work. Okay, all right. So now I'm getting closer to what I'm trying to prove. So what I'm thinking, okay, I want to get down to just angle 1 is congruent to angle 2. So I don't really want the angle 3's in there, but hey, what if I just subtract the measure of angle 3 from both sides of this equation? Because if I did that, then those will just drop out, right? And then I'm down to the measure of angle 1 is congruent to the measure of angle 2. Okay, so I subtracted the same thing from both sides of the equation, so that would be the subtraction property of equality. Okay, and now this is very close to what I was trying to prove, but it's not quite the same because I have the measures of those angles are equal rather than saying the angles themselves are congruent. So, but I know, hey, if the measures are equal, then the angles are congruent. So I can say angle 1 is congruent to angle 2. And the reason I can do that is because that is really the definition of congruence, right? If the measures are equal, they're congruent. That's what congruence means. So I just use the definition. A lot of times for definition, I'll just put DEF. And a lot of times for congruence, I'll just write this. If you want to write out definition of congruence, go for it, but that's how I'm going to write that a lot of the time. Okay. All right, on to page 2. Got some more proofs. 2 more. All right, so this time part of our given info is this picture. Okay, and we don't have to copy the picture into the proof. You don't need to do that. It's just, it would be a pain. So if there's written info, copy that in for sure, but you don't really need to. That's just giving you the setup there. I guess it's giving you the measures of those pieces, but I'm fine with you just using the written given in here. So I'm going to say T is the midpoint of SU. Okay, and that is my given info. So I haven't done any thinking. So even if you're totally confused about the how the proof works, you can always get in the first step. It's just the given info and write given. Okay. All right, and that'll get you somewhere. Okay, so now we got to start making sense of this. So it tells me that T is the midpoint. So sometimes that info is in the picture already. Here it's not. I mean, T looks like it's the midpoint here, but I don't know that for sure looking at the picture. So I'm going to put that info into the picture. Okay, now T is the midpoint in the diagram as well, right? Because I put those little congruence parts. Okay. So then I'm thinking about, well, what does that really tell me that T is the midpoint? That tells me that these two measures are congruent, and that means 7x is going to equal 3x plus 20, okay? So what I really want to do first is to say that the two, and this is a little picky, but I want to say first that these two segments are congruent. So I would say ST is congruent to TU. Just like I put in the picture with those marks, right? And the reason I knew that is because they told me T is the midpoint, and I know what a midpoint is. By definition, it cuts a segment into congruent segments. So this is the definition of midpoint. Okay. Now what I can do with that, since those two segments are congruent, well then I can say, well, 7x then equals 3x plus 20. Okay, and honestly, you know, if you just put this in step B, 7x equals 3x plus 20, and put, well, that's by the definition of midpoint, I wouldn't be too upset about that. I'd be pretty happy with that, because you got the idea. It's just you didn't say the names of the segments first, and then translate it into the expressions, okay? So it's not the worst crime if you do that, but technically, really, we should start with this, then substitute in the expressions. So I just kind of gave it away. I substituted in the expression for the name of the segment. Okay, so I used the substitution property. Substituted 7x in for ST and 3x plus 20 in for 3x plus 20. Okay. All right. Moving on. Oh, and I'm trying to prove what solve for x here, really, right? So I'm just gonna, from here on out, I'm just gonna solve this like an algebra problem. So next thing I would do, I want to get those like terms together. So I'm gonna subtract 3x from both sides. That'll give me 4x equals 20. And that was the subtraction property of equality. Okay. And then next I divide both sides by 4, so this is going to be the division property of equality. Okay, there we go. And all right, last proof. This one has a diagram again. Okay. So angle 1 and angle 2 form a linear pair, and I can actually see that in the diagram, right? And then measure of angle 2 plus measure of angle 3 plus measure of angle 4 equals 180 degrees. That's all my given info. Oh no, it's off screen there a little, sorry about that. But so far all I've done, copied that given info in there and written given. Okay. All right, so we've got a linear pair down there. That means they form a straight line, okay? And then the three angles that are inside the triangle have a sum of 180 degrees. If you know something about triangles, that happens with every triangle. The three angles are going to add up to 180. But there it is in the given info anyway. Okay. Okay, so what I'm going to do first, you can always do something with the given info. So I'm thinking, well, what does this really tell me that those form a linear pair? What can I do with that? So what I can do with that is say what those two angles add up to. Since they're a linear pair, they form a straight line or a straight angle, and a straight angle is going to be 180 degrees. So now I can say the measure of angle 1 plus the measure of angle 2 is 180 degrees, okay? And I got that because I know what linear pair means. It means two angles that form a straight line that's 180 degrees. So I use the, oops, should say B here, the definition of linear pair. Okay. All right. And then I'm going to think, well, what else can I do? Well, and these proofs get easier the more of them you do, because they follow certain patterns. So I'm looking. I can't really, that part of the given, I can't really do much with that on its own. But now if I look what the equations that I do have in my proof, hey, I've got two things that equal 180 degrees. So that means those two things are going to be equal to each other, right? So then I can say, all right, the measure of angle 1 plus the measure of angle 2 is equal to those three angles added up. Okay. Now I could have flipped this around. I could have written that on the left, but I was just looking at what I was trying to prove, and I was noticing that angles 3 and 4 are on the right and angle 1 is on the left, so I just set it up that same way. But you know, you could always use the symmetric property to flip it around if you need to. But anyways, so I've got those two underlined things, both equal to 180 degrees, so they're equal to each other. So that's going to be the transitive property again, or and these are all equations here, right? So the transitive property of equality, or you could say substitution would work as well. Okay, so once one of them is equal to 180, you can substitute into the, say, like I could put the angle 1 plus angle 2 right there in for the 180, and then I got this equation. Okay, so you don't need both of those, either one works though. Okay. And now I'm looking at this, it's starting to look a lot more like what I'm trying to prove. The only thing is there's no angle measures of angle 2s like there are here, but hey, I can get rid of those pretty easily because there's one of them on each side. So if I just subtract the measure of angle 2 from both sides of the equation, then I'll be in good shape, right? So I'm going to use the subtraction property of equality to finish this. Okay, I subtracted the same thing from both sides of the equation. Okay, and you know you're done when your final statement says the same thing as what you're trying to prove. So that's the end of the proof and the end of the section. I will see you next time.